Hello, today I'm going to talk about a computer graphics topic called ray tracing. So let me start out by giving a little bit of background about ray tracing. So initially in computer graphics we focus on high performance interactive graphics, and these tend to fall in the category of rasterizing methods. So OpenGL uses these rasterizing methods to render 3D images really quickly. These 3D images are based on polygonal meshes. They send them through the graphics pipeline, and we get these high quality interactive graphics that you often see in games and CAD and that sort of tool. But there are drawbacks to to these methods because the quality tends to suffer. Additionally, if you want to incorporate things like shadows and reflections, refraction, additional realistic effects, it starts to really slow the performance. And so the benefits of performance start to erode, especially as we aim for more realism. So it's clear that essentially if your aim in computer graphics is to go for realism, using these traditional rasterizing methods is not as flexible as we'd like. Additionally, within rasterizing methods, every object that we deal with has to be a mesh, which means even for a sphere, we have to have a certain number of points that define the perimeter of the sphere. So if we zoom in on the sphere, we're going to see incontinuities. And so essentially we have limitations on the types of objects we use. We can't just use the mathematical notion of a sphere. We have to use the mesh approximation of that sphere. So on the left here, this image, you can see our traditional rasterized 3D graphics image, and it looks relatively realistic, right? A sofa, coffee table, that kind of thing. But we're missing a lot of kind of things that we'd expect. So, the image on the left is something we'd expect from a computer game. The image on the right is actually something we might start to see as something that's close to real. And how do we get the image on the right? Well, we use a technique called ray tracing, and that's what this lecture will be all about. So ray tracing is really based on understanding of the physical properties going on with light and trying to model those in a computer. And this approach is different than the rasterization approach that we've seen that OpenGL uses. So this image you can see here is a fully digital image. Everything in this image is completely digital. It obviously is based on the real world, but it's ray traced, and you can see the realism. You can see things like glass, refraction. You can see liquids. You can see the reflections of the specular reflection of the light, shadows, all these things. And really, ray tracing allows us to accomplish all of these realistic effects in one rather simple algorithm. So how do we do this? Well, it comes down to a simple understanding of the physics of the world. So if we understand that lights, cameras, and surfaces all have photons as their common denominator, lights emit photons, cameras absorb the photons, surfaces reflect the photons or absorb them, we can use this photon common denominator as the root of our algorithm. So what is a photon? Well, as a physicist, a photon is a quanta of electromagnetic energy. Some may call it a particle of light. That's what I like to think of it as in this context. In reality, photons can be particles and waves simultaneously. For modeling in computer graphics, we frankly just ignore the wave behavior. That certainly could be incorporated later, but it's unnecessary to be able to reach the levels of realism that we like. So we really focus on simulating these photons as particles. So how do we do this? Well, we really model them as the mathematical notion of a ray. So a ray has a location, a point, and a magnitude. And so it's shown here by this arrow. We have a point, a location, and a magnitude. So the idea of a photon starting at one point and continuing in a certain direction. So cameras and eyes we kind of use interchangeably in computer graphics. They generally work in the same way in the physical world. They have an image plane on the back of them, although in the case of an eye, it's not really a plane, it's a curved surface, but those surfaces absorb photons, and they take that photon information and they translate it into something that's useful. In a digital camera, it turns it into pixels. In an eye, it turns it into electrical impulses that our brain interprets as sight. There are differences between these two systems. that we can talk about a little bit, but the reality is we can model them as one system, and the differences that happen really are not as big of a concern. We can still get really much more realistic pictures out of this model. So how does this model work? For those of you who aren't photographers, let's talk a little bit about this. So cameras have an image plane that sits behind the lens of the camera. So you can see in this image, light enters our lens, and light obviously is made up of multiple components. So you learn the colors of the rainbow. Any color of the rainbow actually can come in. It goes through some sort of lens, and that's what allows you to zoom in and to focus the light and that sort of things. It goes through filters potentially, and then it hits a color sensor. And the color sensor, the two major ones on the market are CCD and CMOS chips. You can learn more about those in a computer engineering or electrical engineering class, but essentially what you need to know for this is they take that information, they turn it into numerical values that determine essentially the amount of red, green, and blue in the light source. Eyes have a curved plane. We don't really interpret it that way, but they do the same sort of thing. We still see the electromagnetic spectrum, and so that's what we turn into what we see. So the model of the universe that we're working on here is that we have a light source, such as this light bulb. That light source emanates light on objects like the rabbit, the teapot. That light bounces off those objects and into our camera or eye. And then that's what renders the image on the back of the camera, and then allows us to take a picture of our scene. The problem with the notion of this model is that we could certainly implement this model. We could take a ray from our light source here, and we could take multiple rays, many rays in fact, and model all these rays bouncing into our scene and bouncing around. And some of them would hit the camera, but the vast majority wouldn't. So think about it this way. The sun at the center of our solar system puts out many photons. It's a very energetic object. It's putting out lots of photons, and only a very small fraction actually hit the Earth. So in the same way, we could be modeling lots and lots of photons, not knowing where any of them are going. We have to model them all to really see which ones are actually going to hit our camera, and that's can be very inefficient. So we can do better. And the way we do better is we actually turn this model around. Instead of shooting the light or the rays from the light to the camera, we shoot them from the camera to the light. So we start out with rays that start at a location of our camera. They go through an image plane, we'll see in a moment. They go into our scene, they hit objects, and then we calculate the angle of refraction, or the angle of reflection off of those objects, and we essentially trace them back to a light source to find out what color they should be. So this is the concept of ray tracing. So you can see here we have our camera. The camera actually, right in front of the camera, we find an image buffer, and this image buffer then is a grid of pixels, and we shoot rays through this grid of pixels into the scene, and depending on what the rays hit in the scene, then that tells us what to color that pixel. So essentially we get a 2D image plane from shooting these rays into our scene. And you can see if we have more pixels, we just need more rays, and that allows us to get a higher resolution image. One big difference that I'll ask you to note about this is that the image plane in this case is actually in front of our cameras, where the image plane in a traditional camera is actually behind the actual lens of the camera. It turns out we can model that too, actually. It just, the math is a little bit simpler to put it in front, and we still get very realistic images this way. And so this is really adequate for us to be able to do at least introductory ray tracing. So yeah, in practice, essentially, we're taking a ray from our camera through our image plane into the scene, and then once it hits an object in the scene, we have to determine whether it's in the shadow, whether it's hitting an object, whether it goes to the light source, what the properties of the object are, all that kind of thing. And so while we do a little bit of hand waving around this, the reality is the easiest way to determine whether a ray hits an object and when it hits the object and all those sorts of things is to use a parametric form, the equation of the ray. So we define each ray as a parametric form where 0 times 0, it starts at the camera, and we essentially calculate when that ray is going to hit an object. We actually test it against every object in the scene, and then that allows us to determine which object it hits first, because any ray may hit multiple objects. It actually can hit a single object multiple times. So the geometry of this is relatively straightforward. Essentially, we can look at our camera eye here, look at the height and width that we want, and as well as the resolution, and then that defines our number of rows and columns we have of our frame buffer, that or image plane that all these rays are going to go through, and then this gives us our angle of that our camera's views at, and all that sort of thing. So we can actually use a very similar model of the camera that we've used in other graphics approaches in OpenGL previously. So this is a really kind of a simple translation. What we really need to do here is keep track of which row and which column we're in to be able to make sure we're using the correct ray. That allows us to calculate the angles, so we know which how to create the parametric form of the equation. So let's look at some pseudocode. So the pseudocode for ray tracing, we essentially start by defining our objects, our light sources, the camera, essentially placing them in the scene just the same way we do traditional graphics. We have to set the scene first. Then we have a doubly nested loop. This is almost always a doubly nested loop where we go through a number of rows and columns, and within there then we build one ray at a time. So we take the ray from the camera through our frame buffer, through the pixel we're going through in the frame buffer, and into the scene. Then we take that parametric form of that ray, we test it against every object in the scene. Why? Because we actually don't know mathematically which objects it's going to hit and which object it isn't. So you actually have to test the ray against every object in the scene. So you can see here, if you have a really complicated scene with a lot of objects, this could get computationally expensive. And that's one of the interesting challenges we have with this model. But we still test against every object in the scene. Once we've tested against all the objects, then we can find the object that's closest to the camera or the eye. We know that's the one that hits first, and that's the one we care about. So once we know that's the object it hits first, we use the parametric form to find exactly where it hits the object. We find the normal vector at that point of the object. We can then calculate the reflection. Then we can trace that ray to the next place it bounces against another object or to a light source. And ultimately then, once we trace that ray back, it may be several steps. This actually often step 5 here is often its own loop where we're tracing that back many times. But eventually, once we find out what that ray is and what it's hit, then we can then determine what color it should be. So then we put the color in that pixel and we go to the next pixel. So next, what I'd like to do is show you a short video about real-time ray tracing. So traditionally, ray tracing prior to kind of prior to essentially 2010 or so, there really wasn't enough horsepower in modern computers to do real-time ray tracing. We were ray tracing on the fly. But now it really is possible. So I'm going to show you a video of just that.
Hello, my name is Mark Peters, and I'm a technical marketing engineer of Intel. Today I'm going to show you a demonstration of the Xeon 7500 series with a product called Luxury Keyshot. As you can see, the Xeon 7500 system I'm using is a 4-socket server with 32 cores, which means it's processing 64 threads in total. Luxury Keyshot is a product which allows you to do real-time ray tracing on your 3D models and produce photorealistic images very easily and very quickly. Now you can see I just turned off fast updates to show you the performance of the EX system. You can see that the car easily rotates around and you still get great frame rates even with the fast update feature turned off. Now I've just turned fast updates back on so that I can continue the demo and show you some more advanced features that Luxury Keyshot and the Nehalem EX is made possible. As you can see here, we've now put it into the forest scene environment. This is one of my personal favourite environments because you can see here we can do things like turn off the ground reflections, and the longer we leave the system, the more ray traces you get and a greater refinement of the image. So you can see here now that we're getting some photorealistic pictures with all the correct reflection.
So you can see here, first of all, notice the CPU usage here up in the top right. You know, ray tracing is one of these great things that's easily parallelizable. So it actually can take advantage of multi-core and, in this case, many-core CPUs. And essentially, they're able to then allow a real-time ray tracing environments where they can get these photorealistic images. They can establish what is the background, and then as the rays go in there, they can trace more and more rays and refine the image more. And so it really does make for an incredibly photorealistic image. It's hard to believe that this isn't something that exists in the real world. But given enough computing power and a precise enough model, you can really use ray tracing to get a very realistic image. So one of the things you may have noticed in that video is that the car itself was actually reflecting the forest scene that it was in. This was something we call indirect illumination, essentially where objects are actually reflecting light off of each other. If we want to be able to incorporate that indirect illumination into our model, we actually have to do something called, well, splitting the rays. So we may have light that bounces off of one object and reflects onto another, and that essentially means that the rays of light split, which happens in the real world, but unless we model it in a ray tracer, it doesn't really happen. So this is also commonly referred to as what's called global illumination. So you can see, for example, here's a ray traced image on the left that's direct illuminated. So we have a light source on top, and then we kind of have some ambient light source. In a direct illumination model, we get a really realistic effect, right? We can see the refraction or the reflection. But if we use a globally illuminated model where we're considering the light that bounces off of other surfaces, we can see a pretty dramatic effect on the scene on the right here. So you may not have noticed before, but there's a wall that's not shown here that's actually painted green. In this left scene, you can actually see it in the, what's supposed to be essentially a shiny marble or something like that. You can see the green. But over on the right side, now that we have this global illumination, you can see that green color actually reflected onto your scene. You get a lot more definition. Again, a much more realistic looking image, because this is really what happens. In fact, the light source on the top, you can see now, has three-dimensional depth, whereas in the left scene, you can't really see that. So again, we can add more complexity to our ray tracers to get us more precision, although, as you might guess, more complexity does mean more computational power. So what are the benefits we get out of ray tracing? Well, because we're tracing a single ray through the scene, it's actually really easy for us to incorporate shadowing and reflection and refraction. So essentially we can determine how we want to handle this in the core ray tracing algorithm that we showed you. It's just adding more steps. Again, it costs computational power, but the complexity of doing so is much less than the complexity of involving shadowing and other techniques in our traditional methods. So this is a big benefit. Ray tracing also gives us the flexibility to work with a bigger class of geometric objects. So we can now start working with solid or vector objects as opposed to our mesh approximations to objects. So we get a higher quality image, and it also allows us to zoom in on the image effectively infinitely. As long as you have a high resolution object that you're working with, you will have a good looking scene. Whereas if you're working with a mesh approximation, eventually it's going to become pixelated or square or not as precise. Although you can still use mesh approximations. There's nothing that's stopping you from doing that. Now, one of the things you may have also noticed in that video of the Lamborghini is that as the presenter moved the Lamborghini, it started out very grainy looking and slowly got better and better. And as he mentioned, it shoots more rays into the scene. That's exactly what's happening. So essentially, we use this block size. So we can define a ray tracer with a block size parameter. And that allows us to first trace it with a coarse resolution. So we may trace, for example, here, if you have a 16 by 32, our block size is 4. So we trace it 4 high by 8 wide, and that's the picture of the globe here on the left. Then as we get more time to render, then we can trace it at a block size of 2 and then a block size of 1. So the scene on the far right is then a block size of 1. So when you compare them side by side, you can see you get a lot higher resolution on the right. But again, if you're going to do it in block size by a block size of 1, it's going to take much longer than doing it in a block size of 4. And so the idea is you can do this initial block size of 4, and as time allows, you can do a block size of 1. The other thing they didn't mention in the video, but is worth noting here, is that this is so easy to parallelize. If you've got 2 cores, you can literally split the image down the middle and have one core do the left side of the image and one core do the right side of the image, and you'll get effectively 2 times speed up out of 2 processors, 4 times speed up out of 4 processors, 6, so on and so forth. This is essentially called linear speed up, which is really difficult to attain for multi-core systems, but it turns out for ray tracing, it handles this really gracefully. Now, one of the things we haven't really talked about is objects so much. We kind of, when objects are defined, they can be relatively complex, and as you might see here, the example of a torus down here, arrays may enter and exit an object multiple times depending on what the object looks like. So because of that, it can actually be somewhat computationally expensive to keep track of this list of objects that the ray hits. And so one way we can actually improve this is using an extent or a bounding box. You can see on the bottom right here, any object, for any object you can define a box, either a rectangular parallelepiped or a cube, depending on the approach you want to use, that fully encompasses the box. So the benefit of this is that we can essentially render the object within the space, and we can use it to test whether or not our ray hits the object. So essentially, we can test against the bounding box first, and if the ray doesn't hit the bounding box, we don't have to test against the underlying object. And it turns out it's much more computationally cheap to test against the underlying object or against the bounding box than against the underlying object. So we put a bounding box around all of the objects, and then this goes much faster to test all of these things. If the ray misses the box, it must miss the object. If it hits the box, then we test against the underlying object because maybe it will hit the object. So here's an example. We can essentially use a clipping algorithm or something similar to that to be able to test this, this idea. And again, it's all parametric form. So if we have a hit time of our bounding box, then we know we have to test against the rest of the underlying object. If we want to add shadows, this is really not too difficult. It does slow down the ray tracing process, but we do get a lot of benefits. And it doesn't slow it down any more than adding shadows slows down rasterization shadowing methods. So how do we do this? Well, essentially, we just incorporate what's called a shadow feeler. But essentially, what this is a technique of testing a hit point and seeing whether that hit point sits in between an object and a light source. So essentially, if our hit point sits in between an object and a light source, then we only have an ambient light that might exist there, and that's essentially what a shadow is. So we can create an is-in shadow or some sort of similar method to be able to tell us whether or not our actual hit point is in a shadow. If it's true, then we're able to only include the ambient light component of the light source. If it isn't, then we include the full color. If we want to create soft shadows, we just have to define this a little bit differently. So instead of using one ray to determine whether or not it's in a shadow, we can actually use what's called a penumbra or a range of rays. So several rays, either a tight range or a wider range. So the left is a tight range, the right is a wider range. And depending on that, we can then average those values. Instead of being either ambient or non-ambient, we can essentially use gradients to be able to define how much or how soft that shadow is. And that gives us then a more realistic looking shadow, depending on what you want to do. So what's the result? So the last thing I want to show you is one of Pixar's early short films that they've created called Luxo Jr. And this shows a ray traced scene that is really impressive. So you can see multiple light sources shadowing. This wasn't done real time, but it was done in a very impressive way, and I always like to show this. So I'd like you to look for shadows, look for how lights move against each other, and yeah, enjoy. So one of the neat things I'll point out in this video that I like, you should watch the full version sometime, but notice that they were trying to save computational power. This movie came out in the 1980s, and computational power wasn't what it is today. So you'll notice the background is completely black. So why do you think the background would be black? Well, it's because if the rays don't hit anything, then they decided to set it to black. It was much more computationally efficient to have a black background than it was to have a complex scene. So they defined a floor that was relatively small. The objects themselves are relatively small. They take up less than half of the screen, and that actually reduces their computational efficiency. Increases the computational efficiency quite a bit. So that's my speculation as to why they did that, is that would save them a lot of time. I think even with that, if I remember correctly, this took them close to a month of time on a supercomputer to actually render this entire 2 or 3 minute video. So it's not all it's not all cheap, but it's really impressive to see how multiple lights can work together in a ray tracing environment to create a really realistic looking scene. Thank you for your attention.